Got a minute to get going. Hopefully everybody's in good shape this morning. Checking out yesterday. Okay. I believe there's 15 of you here. There's 50 registered. So anyway, online classes attendance is sort of different. I think you're here. You never really know. It's like talking to an empty classroom or a classroom I cannot see. So can someone confirm that you can see me or hear me? Good. Okay. So I am alive. I'm not just imagining myself here. And I think we're uh, ready to start. Let me get some slides ready here. Here we go. There we go. You can tell when I've got a, yeah, Giselle, I'm expecting that. Whoops. So you'll see in my first topic of today, it's going to be questions about the assignment. And so I've got the data set ready, and we're going to go through all your questions about the assignment, about doing different things, and then I'll start in on my material after that. Okay, it's actually not that hard, but this is very new. It's very different stuff, and um, uh, you can actually go through and do the assignment very quickly if you know what you're doing. Um, but it's knowing what you're doing and how to read it. So we'll walk through, and we may end up doing the assignment for the students that are here. Payoff for being present. Um, yeah, I don't know if anybody's been using the Math Help Center on it. I haven't really been in touch with them. It's not like being on campus. I know a number of the students that are working there, but they haven't been corresponding with me. But let's walk through some of the questions you've got, because I've been getting quite a few emails. And if we can resolve it, at least for the 15 of you that are here, I think that's going to be useful. So uh, let me just go through my pictures of today. So when you see the background behind me looking white, it means I'm in Kingsburg at our cottage. Um, and when it's dark, I'm at home in Halifax. So it's a tiny cottage, but we've got a deck that's probably as big as the cottage is, just to enjoy the outdoors. It's I think last class I showed you a picture of a point of land called the Hell, and big waves were breaking over the tip of that point. And there were a lot of big waves, leftovers from the hurricane that had passed well south of us. And this is looking out at the Hell at sunrise this morning. As you can see, it's pretty quiet. And in fact, when going on our morning walk, uh, you could barely hear the waves at all. Normally, you could hear them all the time. It's very loud, actually, but I could barely make them out. What I could hear loudly was just my feet crunching on gravel, um, but that was the only noise. I could hear some birds and a few squirrels. There were a lot of deer out this morning. There was about a dozen in one field, and they look funny. I don't know if you've seen deer close up, but they've got a very narrow face and a big black nose and big brown eyes, and they have these ears that stick out. And when you walk by and they're a distance away, they're very shy and will generally run away if they're at all close to you. And you just see the tail as they bounce away. But they'll just stand there, stare at you, absolutely frozen. They won't move. It's just, they're just like absolutely frozen. And you've got this, say this morning, a dozen deer standing in the field looking out at us. It was fun. Yeah, Jacob, we're going to do it. We're going to work on assignment 3. So, and this is a little bit later this morning, and you can see all how the fall is changing things, and much more light out now. It was bright sunshine just off to the left of us. So, questions about assignment 3. Why don't you, let me just go and here is assignment 3. I'm sharing my screen here, but let me just make this so we can see it. Questions. And and I'll make them bigger. And we'll walk through these. Sound like a plan? So first thing is the data file you've got for the housing bubble. And it's a big file, relatively speaking. So we've got quite a few different variables here. And if we keep scrolling across, we have price, the land value, the building value, total assessment. This is American data. In Canada, we generally don't separate land and building value. It's just one number we have for assessment. And some of these variables, I'm not sure how available they'd be. If I wanted to scrape and collect a bunch of Canadian data, there is a website you can go to. Am I talking? You can't hear me, Aster? That there is a website, at least for Nova Scotia, that is very informative, and you can find out about every property in Nova Scotia, all kinds of detail about it. And it's quite fascinating. But you can get historical information on assessments about properties, when were they last put on the market, and what they sold for. It's very rich data. But anyway, here's the data that we've got here. And I'm going to presume that the city that is doing assessment and trying to put a value on houses is got access to only some basic information about maybe square footage and maybe the age of the structure that's there. So we're only going to use a few variables. So what I've suggested you do is go take these guys. I can take all of them, get me started, and put them in a new sheet. Okay. And I'm just going to take out the ones I'm not going to use. Let me take those out. And condition. And I don't need these, but is this a formula? No, it is just a number. So we don't need these guys. Okay, so this is the data set I'm working with. And stop me as you go along if you're confused as to what's here. So let me make my data bigger so you can see it. The first thing I think it asks us to do is do a scatter chart. Okay, but we want the price on the vertical axis, and that troubles people at the outset. Watch out with Excel as to how it wants columns to do things. So in this case, I want to have the assessment on the horizontal, price on the vertical. And if I just go and grab two columns, tell it insert, do a chart, it's going to give me a scatter chart. But what's on the vertical here is not price, it's assessment on the vertical and price on the horizontal, because it takes the one on the left as being the one on the horizontal axis. Some of you have been saying, well, I'll just switch the axes. Switch. This isn't row and columns. These are axes I'm switching columns around. So if you go and do this, you get an error message. Okay, you can't do it. So what you have to do is go and cut this guy out and put him over here. Okay. And let me get rid of this picture. And I know I've got it the right way now. I hope. See, the thing it puts as being up here is whatever's on the vertical. Now I want you to put in labels for the two axes, and that will come out, okay? And so I've had a mix of people emailing me. Some have gotten this piece right. They've sent me their spreadsheet. I've seen that bit, and then we moved on. But others got this, then tried to flip it and couldn't. And that's because it doesn't allow you to do that type of flip, okay? So what else does it tell me to do? Because we're just trying to get this started. And people, what's the correlation? Okay, how do we get correlation? Let me get data set back. There we are. So if I want correlation between the two, there, and people have been getting this. Nobody seems to have trouble with correlation. I do data analysis. I do correlation. And my columns are G and H. So G and H, and I know it goes to row 1978, 1978. And I'm just going to put it over in column J. Okay, so I can see it. Oh, there it goes. And there's the correlation, 0.94466, which is a fairly high correlation. You can't find the data, McKinley, that on Top Hat, it should appear with your assignment. It's posted. You can't share the screen. Can't find the data. You mean you can't see what I've got? If you're in, I can't show you in Top Hat. Well, we're in the middle of a presentation. Don't think. Nope, I'm stuck there. I'll get back to me afterwards about that bit then, about not being able to see the data set or get the data set. But you should be able, can you see my screen? Yes, okay, my screen is being shared. All right, so I'll show you how to get the data afterwards. And anybody that's still having trouble, email me on that. So that's my correlation. You're asked to comment on it. Okay. And are they good predictors? Well, it's a good correlation. It asks you now to fit the regression function. So I'm going to do that here as well. Okay. So for that, I go up to data. I go to data analysis. We're using pre-crisis. Oh, I picked post-crisis. Did I? No, I didn't. Am I in post-crisis at the moment? Where did I copy my, silly idiot. I seem to have gone and copied did I copy my data on top of, yeah, ignore this. Yeah, let me just go back. Make sure I've got this right. You've got a good question. So I was supposed to take pre-crisis data, which I did, and I'm supposed to put it in sheet 1, which it seems I didn't. So let's make sure we're doing this properly. Thank you for the correction on that. And I hope I haven't lost everybody because of my mistake here. And these ones I didn't want. And I took this guy, I cut it out, put it over here. Okay, and I did my correlation. Let's go back and make sure we've got correlation being done properly. G and H, I put it in J1. Yeah. And I get that 0.94466. Let me make it bigger so you can see my screen. Okay. So that there it is for me in terms of where I am at the moment. I'm not sure what you mean about don't have that button. Which button? You have to be very specific. So now I'm using the right data at least. So if I was going and doing the regression analysis to go and see how well it predicts, I could build a function using regression. Now price is in column H, and assessment is in column G. I don't need these to be to the left and to the right like I did with a scatter diagram. Doesn't matter where it is, but because I'm giving the locations. And I'm going to put it in J5, so I can put it on this screen. And I'm going to ask for my residuals down here at the bottom. And just get in the habit of just automatically asking for residuals. So this model tells me that the model explains, whatever that means, 89% of the variation in house prices. What does that mean? You could ask yourself, how good are the predictions of price based upon assessment? So if I have a house that's assessed at $50,000 and I make a prediction, do I expect that prediction to be fairly close? Well, might it be $5,000 higher than the assessment, or 5,000 lower, or 10,000? Well, that standard error says it's about $17,500. So don't be surprised if your predictions of price are going to be off by about $17,000 either way. So it's, predictions aren't that great. Not as good as we might have thought. And they could be off by a lot more. It asks you what's the equation of the regression line. That's what these coefficients are. And if you can read my screen, I'll type it out as text. The equation of my line is going to be estimated average price. It's an estimate, first off, and it's of an average, not an individual house. It's about average houses, is equal to $8,174.90. That should be an equal sign. Excuse me. Okay. And then going to be plus 0.94 roughly. I'm rounding it off. It's this number here. Okay. I'll get back to my typing here. Times that what the total assessment is. That becomes my formula that I'd use to go and try to predict the average price. And if I look at your assignment, it says, take the output, put it there. And I ask you then, well, try to predict what the selling price would be for a home with an assessment of $50,000 and what you think the selling price would be of a house that has an assessment of $200,000. And so how close is the average price to the assessment in each of those cases? That I've asked you What does the intercept mean, and what does the slope mean? And those are awkward questions. I think they'll be hard for you to come up with a good explanation. But try. I'm just curious as to what you think. What does, in the equation of a line, what does intercept represent? Draw a little picture for yourself of these two things and ask yourself, what is it telling you? So if you had, and if you want to see what that looks like, let me put in my chart here. Okay, here's my scatter chart that I get out of it, predicting price, and this is assessment along here. Okay, and I'm going to do a quick layout, and I'm going to have to pick this one over here. Okay. Oh, no, I didn't want that one. I wanted this one. Okay. Let me get rid of this, give myself more room, and I'm just going to move this over. Whoop. Oh, come on. Move over a little further. And make yourself bigger so you can see it. Oh, this part anyway. Whoop. That was the equation I gave you. Here was the intercept. That's the slope. This is x. That's y. So I've got a line going up here. It starts, this is 100,000. It starts at 8,000. Okay, and it slopes upward. Explain to me what the 8,000 means, and explain to me what the 0.9395 means. I've asked you to make two predictions, one for a house that's way down here, okay, and so one that is, I want right here, make me a prediction of that guy, and make me a prediction of a house that's right here. And you're going to be predicting where the line is, okay, where the average is for the homes. So it's the average of this scatter here and the average of that scatter there. You get it just by putting the numbers into this equation. That. And then I just want, you think homes are being treated equally, that sort of thing? And then if I was making an actual prediction for an individual house, to put another point on the graph, how far off above and below the line do you think it's going to be using the empirical rule with the 68%? We had empirical rule, we've made reference to it all the time since about chapter 2 or 3, I think. So you may have to look back if you're forgetting what empirical rule is all about. Any questions about question 1, or if I answered it, or did I just confuse you no end now? You thought you understood it, and now you're confused. Any comment? Thomas is typing. Maybe. No. Maybe. Can you do the equation in Excel? I'm not sure what you mean by that. I've just typed it out. I just want you to write it out by hand on your paper. Okay. You don't need to type this sort of thing. I'm typing it so that you can see it because I can't write on my screen. I don't know how to do that yet. No, you don't need to have the line, Giselle. I put it in there so you could see what that line looked like. There's a way of formatting a scatter chart so it puts the line in, but you're not expected to do that. If you have time, and I know you're busy because you've got lots of courses and doing stuff online is hard, So I'm not expecting you to have time. But if you did, if you're doing some of these things, you may want to explore what can you do in terms of changing charts or formatting them and that sort of thing, because it's a useful skill to have. At the end of the course, the last topics, we're going to talk about how to make really good charts, things you should do or shouldn't do. But I'm trying to keep away from that for now. No, well, to make your predictions, don't make them from the chart. You've got a formula that you can use. So put, where was I here? So can I just throw that out and get back to where I was? I think where I typed a formula. If I take, so if I was doing it for 50,000, okay, I would go and say equals, and actually I'm going to cheat. I'm going to take slope plus, or sorry, the intercept plus the slope. And I want 50,000. Excuse me, I did something wrong here. Times, whoops, it said J of 50,000. There we go. And so my estimate of the price will be 55,000. Trying to read that off the graph, couldn't, because it's just not detailed enough. And then if I wanted to do it 200,000, I'd go back, do the same thing as there, and I just change the number here, 200,000. Now I get 196 at a different value. Okay? So that's basically all you're doing with it. All right, let's go back here. Let's look at question 2. Okay, and if you're okay, 1H was the opinion one, wasn't it? 1H. Yeah, what's your thoughts on that? And so express whatever you think. Often with the comment questions, I'm just looking for you to reflect upon it. We have a tendency to, and I think university is bad at actually developing this in you, to do some analysis, you get a result, and you just say, there it is, move on, write down the number. And we don't stop and reflect upon what we've got. Does it make sense? Is it reasonable? Is it a surprise? What I expected, not what I expected, or I had nothing. I had no idea what was going to happen. So this is the outcome. All right. But they don't think about it before they move on. And it's a very bad practice that we do too much of our work. At times, I say if you can avoid thinking, do so. So if a computer will do the stuff for you and save you some work, then that's good. But with your results, before you move on, think about what you've got. And I think in the management science area, and I think it happens in accounting and finance as well. I don't know about the less technical subjects, but I'm afraid people often work out the answer and then just move on and don't reflect upon what is it? Is that good, bad? Is there any problems? And many times there isn't. It's just fine. But think about it first. I'm not always going and make you think about something because it's wrong. It may be it's right. Okay. Next bit I asked you is about a correlation table. Oops. How to do that? Yep. How did Zoom get on? So let's go back to our data and my sheet 1 here. And to be honest with you, I would go and take all of these guys, copy them, start a new sheet. Okay? And so I would go and so I don't, and some people have sent me their spreadsheets and they've done this. They've had Q1, maybe they've even had parts of question 1 or parts of question 2. And this way they keep themselves organized So if they have to go back and change something, they haven't overwritten it with something else. So here's my data again. And I've asked, find me some correlations. I'm looking in particular about acres through the car. I don't care about assessment now. I'm not going to use it. So I'm going to go and try to do my own predictions of price. I'm going to I go back to correlation. The data is in column, well, actually, since I've got assessments in here, I'll leave it in there. But actually, no, just hold on a sec. I'm not using this anymore, so I better get rid of it. There we go. So this is all the data I need for question 2. And I'm going to go to data analysis, I'm going to correlation, and I'm going to go from columns A to G, not H, and all the way down to row 1,700 or 978. And I'm going to put my results over here in I so I can see them. Okay. And I get this. So again, what is a correlation table? It's the relationship between different variables, like between acreage is 0.33, above space 0.71, hey, that's pretty high, basement 0.35, deck 0.27, age, it's minus 0.4, and the size of, I guess this is the garage, is 0.49. So lots of things seem to be correlated with price. And you can also look to see what's correlated with each other's. On a bigger property, are there bigger houses? Yeah, maybe a little bit. Um, that um, that among these different things, is there much? And most of these variables, there doesn't seem to be a strong correlation. Age and garage seem to be tied together, but the others are relatively small, some positive, some negative. Okay. So then I've asked you to, okay, take the one with the highest, that's above space, and take price, and go and, where was I? I want to insert a chart. It suggests a scatter chart, and that's what I want. So there's my scatter chart, and price is on the vertical axis, and this is how many square feet are in the house. A small house in Halifax, little tiny ones along Bears Road. They're little post-war cube-shaped houses. They're very, very small. They're between 1,000 and 1,200 square feet. So this is a tiny house. Something that's down here at 500. Most of you, if you're in an apartment, you're in a place that's bigger than 500 square feet. A small one bedroom is 500 square feet almost, not much bigger than that. Um, that, but if you're into a really big palatial house, yeah, they get up here. And I know of a few people that have homes that have 4,000 and 5,000 square feet. They're big, 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 big houses. I can't imagine anyone wanting one that big. I wouldn't want to clean it. But it looks like most of ours are in this range. But as you get to a bigger house, you do get a bigger price, higher price. Um, that um, that this one, Giselle, you were asking about need price for correlation. Well, you are trying to predict price. So in your correlation table, you're going to need to have price because you want price. How is it correlated with the other variables? And this bottom row tells me how it's correlated with the other variables that are up above. So that's why I need that one. Okay. That, yeah, would I have confidence in making predictions? Okay. That I ask you fit a model. So we could go back here. I'm throwing it all in together here. I want to do data. This I should probably be doing in different worksheets, but I just want to show everything in one place while we're doing it instead of jumping from sheet to sheet. So this one, price is what I'm predicting. In all these ones, it's always going to be price. Okay. Are you complaining? Yeah, you're not supposed to come in here. No, 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 no. Okay. Ah, cats. Now I'm going to use just above space to make my prediction. So that's my X variable, and that's in column B. And I've got labels. I've been asked to get my residuals. I want to put them somewhere down here. So let me do I10. Put it in. Keep it all on this page. Okay. And so this becomes my model that it's got an R square of 0.5. Not really high. You know, it's not a great model. And that we saw with our scatter plot. It's not a great model. That it has a standard error of 37,000. Means our predictions of price just based upon the size of the house, the square footage of the house, could easily be off by 37,000, could be off by 50, 60, or 70,000. That's not a very accurate prediction for a house that might only be worth 50 or 60 or $70,000. That and the model says the price of a home is $13,000 plus $88 times the number of square feet. So there you may be able to interpret what does the 88 mean? It's the slope. It means for every additional square foot in the house, you make it 1 square foot bigger, a little tiny bit. The price of the house on average will go up $88.64. That's what the slope means. And the intercept means if you had a house, a property that had no house on it, so the square footage was 0, that's basically the land value. Then I guess it says it would be worth $13,000. So the average home that didn't have a home would sell for $13,000. And I asked you to just produce these residuals because we may use them next. So that's why I asked you to save them, but you didn't need to show me them in that question. So I've got that. I've got my R square. I've got the equation of the line. And now I want you to look at the residuals. Okay, lots of steps here. So take this table. You can take all the columns. There's a lot of them. Come on. Almost at the end. There we go. Copy them. And I'm going to put them in a new sheet. Okay. So these are the residuals that I had. Make it bigger so you can see my. And let me go back to my data here that I had. Okay. So, and actually, I'm going to take. Do I want? Well, let me just take all the data for now. Okay. And put it in my new sheet. Oh, I don't need this anymore. Okay. I'm not going to use the above space anymore. Okay. So, well, I can leave it in or I can throw it out. I didn't say you couldn't leave it in, But I want you to find the correlation between the residuals and acres, basement, deck, age, and car, not price. We've already taken into account of above space into price, so we're not looking at correlation with price. But I want to know, of these variables, we knew that our model didn't make great predictions. If I look back here, question 2, that there was a residual plot that I didn't use. Okay. But look at this. And just to give you an idea of what this plot means, it says here's, say, a 2,000 square foot home. I should expect that my predictions about price could be off by as much as about $150,000 in one direction or $100,000 to $150,000 in the other. This is big amount of error, huge amount of error on either side here. Okay, that being off by over $100,000 each way seems like not a very good prediction. So I'm trying to get these numbers smaller. So what I'd like to do is go and do some analysis on what's the correlation, what's the relationship between the mistakes I make. So the mistakes I make is in column C, and the variables I've got. So they go up to column I. Okay. I'm going C and all the way across. I'm leaving above space in there. And I'm going to put all of this stuff in column L1. Oops. That'll work. Oh, there it is. It's over here. So the key thing I'm looking at now is the residuals. Okay. What's related to my residuals is acres has a positive relationship of 0.2, meaning if the land is bigger, the house is on, then acres could give me more information that the error that I'm making is bigger than I make. So I could take that in. With above space, you get E minus 15. That means 0.000. There's no relationship between the errors and above space because I've already adjusted for that square footage. Okay, so it's essentially 0 at the moment. With basement, 0.397. Hey, that's fairly important. With a deck, 0.23, so bigger deck. With age, it's minus 0.5. And with the size of the garage, it's 0.32. This one's negative, but in absolute terms, it's the biggest number. So the correlation is strongest with age. And I think I've told you that as an answer, just to make sure everybody does the same thing. That you should find that age has the strongest correlation. So I want you to fit a new model, and I want you to see how good it is. So I've got to fit a new model. Okay, it's going to use age and above space. Above space is here, age is there. Let me go take these guys. I'm going to create a new sheet. Put it in there. I don't want this and this. Get rid of them. I don't need this one. Get rid of that. So here I am. Now I've got how the square footage, the age of the building, the price of it. And so I'm going to fit a new model once again. Going back to regression. This time my Y value is in column C. And my X is in column A and column B. Okay. And so then I can hit Oh, and I'm going to put my output here in E1. Oh, no, maybe E1. Give me a space. So this is my new model. My R-square before was 0.5, and now it's 0.63. So it's a bit bigger. Good. That's an improvement. Still a long way to go to get to 100%, but it's good. My standard error was $37,000 before. Now it's 32. It's still a big number, but it's smaller. So my model is getting better. May not be happy with it. We now have, if you had a house that had no square feet and was brand new, it's worth $60,000. That's the average price. And the price goes up by $85 for every square foot. Before we included age, we said every square foot increased the price by $88. So this has changed a little bit. That's what it is. And this one is minus 696. So for each additional year of age, average price goes down by almost $700. Old homes are worth less than new homes. Probably means more repairs, and that's why. So that gives you an idea of what's going on there. And so I've asked you to write out that equation with all of those terms in it. And I'm going to stop there and leave you question 3 to do, where we're asking you to go back and rebuild the model with all the variables in it. So I've got all the different pieces and interpret different pieces of that model. And I hope you should be able to get through that. Okay. So let me stop there, and I want to move into some of today's stuff, and I'll do a little bit of it. So we've done about 45 minutes, and we've got about half an hour to do my material. That's fine. We don't have that much, and if I end up not covering it all, I can always pick it up next week. We're not going to be using Excel heavily shortly, but a lot of what I was going to do today was to start out just reiterating stuff we've done, and this is very repetitive, and it's because it's hard to understand, and so I need to keep going over it, hoping that the more we repeat it, refresh it, it starts to make more sense with each repetition, because this is not easy, I think, to master. And so we're doing 2 sorts of things, or what we've been doing is value estimation modeling, doing it by regression analysis. When will the recording? I'll upload this one. I won't have time. It takes a while before the actual video I can download as a file, and then it takes a while for YouTube to go and upload it again to YouTube, and then it's relatively quick. I just give the YouTube link to you. But I will do it for you after my 1 o'clock class, so at around 2:30, I'll try to have it up there. So it'll have a recap of these things. Okay. We've been using linear regression as a way of estimating a formula that's going to allow us to do these predictions. And I was going to have a discussion, but we're not going to have it. Okay. I was wondering if you could think of other methods of doing this, and I've already posted that in the broader discussion, but I thought maybe we could, instead of bringing up what other people have said already, to bring it up here. That if I wanted to predict a student's grade, that instead of building a model, I might go and look for 20 previous students that were similar. So if I had an art student that went to Citadel High School in Halifax and had a high school average it was between 75 and 80. It was a, what am I saying? I've got a student, went to Citadel High, say it's a female student in arts, grades between 75 and 80. I could go back and look through our historical records to find 20 other students that all graduated from Citadel, all were female, all went into arts, and all had high school averages that were 75 to 80. And then work out what was their average grade in their first year of university. And that would be a way of trying to make a prediction. And I'm going to use similarity to do it. That I posted a discussion question about similar. How do we define similar? I've gone and tried to describe how I'm going to do it, and that might work with some data sets, but it's more complex than that. But anyway, there are lots of different strategies I could possibly take to do value estimation. That if I'm trying to predict the price of a house, I might look to see, well, when did it last sell? Oh, it sold 6 years ago. Since then, house prices have gone up so many percent. And so I'll just take that percentage and multiply it by the last price it had. And I won't look at anything else. Okay? It's a formula in a sense, but it's a very different one from using a regression analysis. And we use a lot of these very simplistic approaches, and often with great success. Having a big, complicated regression model doesn't necessarily work well, especially for things like property appraisals. They just don't. Causal analysis is nice because I can figure out the influence of different variables. That I could look at, if I was predicting students' grades, I could look at the role of your high school grades. I did an analysis of business students, must be 25 years ago or more. Yeah, it's more than that. And we were looking at, the province used to have two different math courses, a science math and a non-science math. And it was going to get rid of that and just combine them into one. They did briefly, and then they brought back science math as being the pre-calculus course. But we were curious as to see whether or not there was a difference as a student did science math versus non-science math in how they did in the business program. So we were doing, in a sense, a causal analysis to see what factors were important in predicting their grades. And as I said, linear regression is far and away the most common way of doing it. We get a nice formula that comes out, and it tells us about each of the factors, how important they are, how much they change, and it gives us ideas. If we could change something, one of the x's, we could predict then what the impact would be on y, and it informs us for making some decisions. But we have problems because often the factors are interrelated, and we have this problem we call multicollinearity. That's just when factors, the different factors we're using to predict, if they're tied together, I can't pull them apart. I have to go and keep them together all the time, which makes it difficult to interpret. Are we getting, oh, no, we aren't. Another thing that we did see, and that was earlier, but it still might apply here. Remember that correlation is not causation. They may be correlated, but it may be some other factor that's driving this. So if we start out with a simple model, that it may be that we think A is causing, B to happen. Because A and B seem to be related. We get a nice scatter chart and they seem to be related. But it may be some other factor that is causing both to happen. This particularly occurs when your data is collected over time. So I have weekly, monthly, annual data for two things, A and B. And when I plot them, they look to be related. But really what's happening is both of them are changing over time in the same fashion, like the funny graph I showed you about spurious correlation. If you, The two graphs, if you had plotted those two variables together, you'd find very, very tight correlation, but it's really time that's driving it. And we've looked at binary variables, how to add that in. We can also do it with variables that have many values, but I said I wasn't going to do that, and we've used up a lot of time already. I'm not going to talk about standard error, but look at some of these sorts of things. We have covered this. That what I'd like to move into is classification models. And classification models are really, really common. They're probably more common than value estimation ones, but value estimation somehow comes up in classification, just like classification may come up in value estimation. That I'm often trying to predict what will a customer buy, or is this a customer that's going to buy something? I'm predicting whether or not you're going to renew your cell phone contract with students. We're trying to predict, are you going to come back again? How are we doing with student retention? And sometimes I'd like to know causal analysis, that universities want to retain their students and keep them. Could I build a model that would tell me why students are dropping out, and then I could go back and change things so they didn't drop out? It's proving to be very, very, very difficult. That often the reasons we can identify are things that we can't change. That the levers we have for change aren't very good. And the data is pretty awful too. It's hard to get really good quality data. In classification, we're trying to, it's like predicting a categorical variable. And most of the time, and all the examples I'm going to look at are binary ones. Are you going to stay or are you going to leave? Are you good? Are you bad? That are they going to buy the product or not buy it? Is this fraud or is this not fraud? Yes, no, yes, no. But we can have classification problems that puts them into many different groups. Is the student likely to go into business or science or arts? That I can have many categories and I can look at how they fit into them. Those models get a lot harder to build, honestly. And they're less common. We're more often than not trying to just fit people into one of two groups, not fit them into many groups. And we'll look at this one. But when you start seeing the different types of strategies, and some of them only work for binary variables, but for some of the others, it could be quite complicated. We will look at one at the end, I think, that can allow us have more different types of classes, different classifications. So as I said, there's the binary ones we'll look at are simple things, that yes, no type things. So, and I'm going to have issues of defining accuracy. How good is my forecast? The ones in value estimation, it's if I'm predicting the price of a house, how closely can I predict the value of that house? How closely can I predict your grade point average in first year? How closely can I predict your credit card balance? How many gigabytes of data are you going to use on your cell phone on average? I'm predicting a number. And so we're trying to see how close to actual that we get. What is errors in classification? In those errors, they're different. They're not large and small errors. That I'm predicting someone would graduate, but they dropped out. I'm predicting that this was a valid credit card transaction, but it was fraudulent. Are those big errors or small errors? We don't think of them in terms of that. We're thinking of being not size, but right or wrong. So when I'm measuring performance, I might be asking, how often am I right? How often am I wrong? What percentage of the time do I make the right classification? Or maybe of the fraudulent transaction, what percentage of them I'm able to identify? Or of the valid transactions, what percentage I identified correctly? I may have, we're going to see, and this will be later, after we finish classification, we're going to look at how do you evaluate whether or not your model is performing well or not. So I'm going to leave that discussion till later, whereas with value estimation, we looked at the quality of the result at the same time as we were looking at the model, as building the model. That because it gets more complicated. That just like we before looked at our small errors, is an error of 1 or of 5 the same as 5 mistakes of 1? What's the relationship between size of error and the cost to us? And with classification, I may have different classifying a fraudulent transaction as valid means I'm going to lose the money there. I've allowed the transaction to go through and the money is lost. There's a real cost to that. What about classifying a valid transaction as fraudulent? That one, that's a different type of mistake, and that will have a different cost to it. Different mistakes have different costs. So we're going to have to look at some of those issues, but we're going to look at them later. A lot of I'm going to start showing you examples of different models, but we're not going to go through calculations of them. I'm just trying to give you the concepts behind them. And because for the most part, Excel, it's hard for us to implement some of these models. The ones I'll start with, you could do, but you probably wouldn't want to. A lot of models involve a two-stage process that I might work out what's the chance this transaction is fraudulent. And if I think the chance it's fraudulent is 90%, I might say, hey, I'm going to reject it. Suppose you came up with 40%. What would you say then? Well, I'm not sure. What if it was 10%? What would you do then? The probability is useful, but then you have to make a decision. It's like if you get the forecast in the morning, what's the chance of rain? You've got to make a decision. Do you bring an umbrella with you or do you not bring an umbrella? Do you wear a raincoat or not wear a raincoat? Based upon the probability, you make a decision. Because you're in a sense classifying things. You're going to classify this as a rainy day or not a rainy day. And what happens if you're wrong and you make a decision? That as I said, it gets a little bit more difficult, but it's done in two stages. So I need two things. One is a way to estimate the probability of rain or fraud or what have you, and the other is coming up with a decision rule. Because just the probability may not be enough to give me an idea of what the decision rule should be. But if I'm just looking at finding the probability, how do I do that? Sounds like value estimation, estimating a number. And can you use regression analysis to do it? So I've got a data set, and let me just show you the data set. It had a bunch of employees. Some were good employees, some were bad employees. And I've classified good ones as a 1, bad ones as a 0. Okay? And I've got test scores. Each job applicant, when they applied for their job, they wrote a couple of short tests. One of them on their basic math skills, arithmetic, could they deal with numbers, percentages, that sort of thing. And another one was on their verbal skills, on their how well they can interpret things, what's their vocabulary like, how can they understand a sentence and digest information that's given to them verbally. And so there are lots of standardized test scores that you can have that test you on verbal and quantitative skills. So they've got test data from this. They want to know, does the test data help them classify employees? So they've taken 20 employees from the past. They took 10 bad ones, 10 good ones. Hopefully that isn't representative of their employee mix. Hopefully their number of, they don't have half their employees being awful and half of them being good. maybe they've got 1,000 employees, and they just took 10 of the good ones and 10 of the bad ones, okay? Just so they had two equal size groups to compare. And they may have tried building a scatter chart of this. But it's strange data that, think about it. Whoops, where'd I go with my slides here? You got this, and I could build a regression model, but this is a strange model. Look at, I did do that. Where did I go? I went and fit a model where I was trying to predict column B, 0 or 1, using columns C and D. And I got a model. It had an R-square of 0.53, 53%. That's sort of like what we just had in your assignment when I just used above space to predict things. So it gives me some predictions. It may not be perfect, but may not be that bad, right? That let's look at interpreting that thing, though. Okay, here's the model. So it's a regression model. So it has an intercept. It has a slope for mathematical score, slope for verbal score. These are tiny numbers, but remember, my rating is a 0 or a 1, and these numbers are in the hundreds. So that's why these numbers are tiny. R square 53%, standard error 0.37. So how well is it working? We've had models, well, before I showed you cases where we could put in a binary variable as an X, but this is 0, 1 for Y. Not predict that the data that I got, I don't have probabilities from the past. I have just 0 or 1, and I'm trying to make a probability from that. And you could look at scatter plots of that. Here is a scatter plot of these are the different mathematical scores. Okay, and are you a 0 or a 1? So here are the bad guys. Here are the good guys. Good guys had higher math scores. Here, the good guys had slightly higher verbal scores. Okay. So, but awful lot of overlap. And if I was to put a straight line, it's a silly straight line. Doesn't make an awful lot of sense. But we can do it. And you can go and look to see how your model performs. I've drawn this the other way around. Okay. Here's the actual rating. Is it a 0 or is it a 1? Okay. And then here's what happened when I made my predictions. I put them back into that formula, and these were my predicted probabilities. Some were negative, can't have a negative probability. And so the bad ones went from minus something all the way up to plus 0.6. And here are the good ones. Good ones went from about 0.3 all the way up to 1.1. Can't have a probability bigger than 1. But this model doesn't understand that. Remember, I was just fitting a straight line, and my straight line could go below 0. Here's one, it goes down below 0, and it can go up above 1. Okay? It's just a dumb straight line. It doesn't know what it's doing. So I'm getting really bizarre results. Let me see if I did it in here to see if I gave you a chart for this stuff. Not there. I thought I did. No. There. Oops. No, these are just residual plots. You know, if I looked at residual plots, they look, hey, nice scatter. This seems to be working just fine. But it's really not. Oh, here it is. Here's my predicted rating. There's my actual rating. And I've just flipped my axes around. It would just, because of the way the data was, it's the opposite of what I just had there. But here is, you know, people that if I drew a line at 0.5, if your predicted rating was less than 50%, then you're bad. If you're better than 50%, you're good. If I had used this on the 20 employees, then these 4 good employees I would have said are bad, or these 2, and these 2 bad employees I would have said are good. So I'll make mistakes. It's not going to be a good model, but this gives you an idea of these are mistakes and these are correct. So it's a very different way of trying to think about errors that you've got. The PowerPoint definitely will be posted. I do that with every one, but sometimes I'm slow, but I'll put it up this afternoon. Do I have any time left? I got 6 minutes. Let me show you some other ideas. This one was crazy because I used a straight line. I can't go below 0 or above 1. What if I put in a curve that went like this and then zipped up here? So if I could have a curve that ideally just went step straight up, and I could do that. I've just drawn a curve, okay? Maybe this is not the right one, but maybe my curve should stay lower here, go up fast, and then level off here. And so used a curve model, a nonlinear model, because it's a step. So I've got a function that has like a step to it. I can't do just a simple step. I've got to do it as a curve. But this S-shaped curve, this is a very common technique. It's a very popular technique. It doesn't work well with this data set, but you'll see that it works well for people at the bottom, people over here on the right, but it gets confused in the middle because the data is confused. But maybe if I've got more variables, it will help me resolve the confusion in the middle. Okay? What is confusion for one variable might not be for another one. And you can fit it. It's called logistic regression. It's not available really in Excel, but that I think in your notes there is a link to if you want to build one in Excel, you can. You have to use Solver. That's a tool that you may have used in Quant 1 for doing some problem solving. It's to explain what the model is really beyond this course. This is how complicated it is. It's got what looks like a linear regression equation in there twice, but it's as an exponent. So this is a very messy looking formula. You don't want to deal with it, okay? But it is nice because it allows us to do causal analysis. I can look at the impact of a math score and the impact of a verbal score separately. So it's got some of that benefits of regular regression for doing causal analysis, though even that, it's complicated to interpret. But it at least tells me which factors are important, which ones are not. But its predictions are awful, okay, that in this data set. But in practice, it's one of the most widely used methods, and with large data sets where I've got a reasonable number of variables to work with, it's had a lot of success. And I'll just show you quickly another one that is common that involves, if I plotted these, and so I plotted this, and I was able to trick Excel into putting blue dots for the good employees and orange triangles for the bad employees. And you'll see the bad ones are down here, the good ones are up there. We sort of figured that out. Good ones had high math and verbal scores, bad ones had lower scores. So the lower the scores are, more likely the person is to be bad, higher scores, good. Can I put what we call a discriminant function? Put a fence up and say if you're on one side of the fence, you're good. If you're on the other side of the fence, you're bad. And I've drawn it as a linear discriminant function, and there's a process you can use for calculating this. There are also methods for making curved functions that sort of wiggle. You've got to be careful about what you're doing with that, but that's another approach. When I get into multiple variables, 3 predictors, I can't show it to you because it's in space, but the methodology can be extended to that. Some methods say, let's not just put a straight line, let's put a ribbon that's wide. It's like, oh, I can't edit this guy, sorry. But if I could take that line and make it wider, how wide can I make the line and still get good results? Okay? And if I can make it very, very wide, then it makes me think it's not so important how I drew the line. I've got a good way to discriminate between good and bad. But if I can only draw a very skinny line, then it's very sensitive to the good and bad. There are different aspects in terms of doing it. Those fat lines are called support vector machines. Yeah, what do you mean by a machine? As I said, this comes out of computing science, and they call it machine learning. So if the machine is learning, then a support vector is a type of machine that learns. It's words that make me uncomfortable, but it's another strategy that's out there. And so these are ones that use formulas, okay? And that I could also have ones that are based upon sets of rules. And we're actually going to do that later on in the course. So we could say, you know, if the math score is above 350 and the verbal score is above 350, you're okay. If it's this, maybe not. Otherwise, this, that, and I can come up with combinations and have it. And I'll have a set of rules. Excuse me. Warning me to the next class is coming up. So I must be overtime. So these are just some of the different things. And in the next class, I'll introduce you to another strategy for doing it. So I've just quickly said, you know, some will use a probability and then a decision rule. Some of them build a function that says if you're over here, this happens. If you're over here, this happens. That can be expanded to a set of rules. If, then this. If, then that. And so it's moving away from a formula towards rules, and we can actually get to a different one that has to do with sort of what I was suggesting in value estimation. I could do it by looking at similar cases from the past. And often that's the way we make decisions, it's based upon experience, which is using past similar cases. But how do we get into that? And as we move beyond that, we're going to need to start doing probability, which is going to be in the chapter after classification. Now I'm finished. So hopefully that was useful. So I zipped through it a little fast, but we can go back over it. It's not critical. I hope that spending 45 minutes on the assignment was helpful to you. And if that's the case on future assignments, then do that. Okay? Anyway, you take care. This is Wednesday. Oh, you don't see me till Monday. So have a good weekend. And keep in touch. You feel less stress. Good. Stress is yesterday I spent time at the dentist for a good chunk of the day. It's because stress is causing me to grind my teeth at night, and I've broken 2 teeth. And I think yesterday I broke a 3rd one. I haven't told anyone that yet. But yeah, stress is affecting all of us in strange ways. So you take care, and tell me what I need to do to reduce your stress. Take care. Bye-bye.